Imagine for a moment that you are driving down a winding country road along the Swiss-French border. It is a scenic route, quiet, unassuming. You pass a standard, mid-sized truck, the kind you might see delivering furniture or frozen food. You wouldn't give it a second glance. But if you knew what was inside that truck, you might pull over and let it pass with a very wide berth. Because that truck isn't carrying milk or mail. It is carrying the most volatile, expensive, and impossible substance in the universe. It is carrying antimatter. Specifically, it is carrying a cloud of antiprotons, the mirrored ghosts of our reality, suspended in a vacuum so perfect it makes deep space look cluttered. If that cargo were to touch the walls of its container, even for a microsecond, it would unleash a burst of pure energy. This sounds like the plot of a Dan Brown novel or a high-stakes heist movie, but it is actually a very real, very revolutionary engineering project currently underway at CERN. Today we are going deep into the story of the impossible cargo. We are going to look at how physicists are building the ultimate thermos to put the universe's most fragile substance on wheels, and why this technology might just be the future of curing cancer. To understand why anyone would be crazy enough to put antimatter on a truck, we have to look at where it comes from. Deep within the massive complex of CERN, near Geneva, there is a facility called the Antimatter Factory. This isn't the famous Large Hadron Collider that smashes things together to find the Higgs boson. This is a place dedicated to the opposite goal: slowing things down. You see, making antimatter is a brute force affair. They take a beam of protons and slam it into a block of iridium. The violence of that collision creates a shower of new particles, including a tiny fraction of antiprotons. But these newborn antiparticles are wild. They are traveling at near light speed, they are incredibly hot, and they are unruly. To do anything useful with them, you have to tame them. CERN uses machines called the antiproton decelerator and the ELENA ring to slow these particles down from the speed of light to a virtual walking pace. They cool them down until they can be trapped. But here is the problem. The machinery required to create antimatter, the massive accelerators, the pulsing magnets, the high-voltage systems, creates a chaotic environment. In physics terms, the Antimatter Factory is electromagnetically noisy. It is humming with interference. But physicists want to measure the properties of antimatter with exquisite precision. They want to see if an antiproton is truly the exact mirror image of a proton. Does it have the exact same mass, the exact same magnetic moment? The standard model of physics says yes, but if they find a difference of even 1 part in a trillion, it could unravel our entire understanding of the universe. It could explain why the universe exists at all, since the Big Bang should have created equal parts matter and antimatter that annihilated each other instantly. We are here because of a discrepancy, and we need to find it. But to find that tiny discrepancy, you need silence. You need a laboratory far away from the thrumming machinery of the particle accelerators. It is like trying to listen to a whisper in the middle of a heavy metal concert. You need to take the whisper somewhere quiet. And that is why we need a truck. Transporting antimatter is, frankly, an engineering nightmare. You are trying to move something that cannot touch any physical object. If an antiproton touches the wall of a container, it vanishes in a flash of gamma rays. It has to be suspended in a perfect void, held in place by invisible hands. This is where 2 pioneering projects come in, Base Step and Puma. At the heart of both projects is a device called a penning trap. This is the thermos I mentioned earlier. A penning trap uses a combination of a strong magnetic field and a weak electric field to cage the particles. Imagine a powerful superconducting magnet, generating a field of about 4 Tesla. This force makes the antiprotons spin in tight circles, preventing them from flying out sideways. Then, electrodes above and below the particles create an electric potential well, gently pushing them back towards the center if they try to escape upwards or downwards. Inside this trap, the antiprotons float in a vacuum that is mind-boggling. The pressure is around 10 to the power of -16 millibar. To put that in perspective, that is trillions of times lower than the air pressure at sea level, and significantly emptier than the vacuum outside the International Space Station. In this environment, an antiproton can circulate for years without hitting a single gas molecule. That is the level of isolation we are talking about. The first project, Base Step, stands for Symmetry Tests and Experiments with Portable Antiprotons. Their device is a marvel of miniaturization. Usually, the superconducting magnets required for this work are room-sized behemoths. The Base Step team has shrunk the entire apparatus down to about 1 ton, small enough to fit on a small flatbed truck. It includes the magnet, a cryostat filled with liquid helium to keep the system near absolute zero, that's roughly -269 degrees Celsius, and a battery bank to keep the electronics running. The cold is vital. At those temperatures, any stray gas molecules freeze onto the walls of the chamber, cleaning the vacuum to pristine levels. The second project is called PUMA, or Antiproton Unstable Matter Annihilation. Puma has a different mission. While Base Step wants to take antiprotons to a quiet room for measurement, Puma wants to take them to a fight. Puma aims to transport 1 billion antiprotons from the Antimatter Factory to a different facility at CERN called ISOLDI. ISOLDI produces rare, radioactive atomic nuclei that decay in milliseconds. These nuclei live such short lives that they can't be moved to the antimatter, so the antimatter must go to them. Puma is a double-zone trap. One zone stores the antiprotons for the road trip. The second zone is a collision chamber. When they arrive, they will release the antiprotons into a cloud of these exotic, radioactive nuclei. The antiproton acts like a scalpel, peeling away the skin of the atom to reveal the internal structure of these unstable elements. It is a way of probing the nucleus that has never been possible before. But let's talk about the road trip itself. Building the trap is one thing. Driving it down a potholed road is another. In October 2024, the Base Step team conducted a historic dress rehearsal. They loaded their 1-ton trap onto a truck. But they didn't load it with antimatter just yet. They loaded it with a cloud of 70 protons. Protons are the matter counterparts to antiprotons. They have the same mass but opposite charge. Crucially, if the trap fails and a proton hits the wall, it doesn't blow up. It just gets lost. They were the perfect crash test dummies. The truck set off from the Antimatter Factory, winding through the CERN campus. This was a white-knuckle ride for the physicists watching the telemetry. Every pothole, every sudden break, every turn generates g-forces. If the jolt is too strong, the magnetic field lines could shift, or the electric potentials could wobble, causing the particle cloud to splash against the walls. Furthermore, the liquid helium inside is a fluid. Sudden movements can cause it to slosh. If it sloshes too much, it can warm up parts of the magnet or induce what is called quenching, a catastrophic loss of superconductivity, where the magnet suddenly gains resistance and boils off all its coolant. To stop this, the trap is suspended on an intricate system of air springs and vibration dampers, similar to the technology used to transport delicate satellites. The result? It worked. The 70 protons survived the trip. The electromagnetic suspension system was robust enough to handle the bumps of a Swiss road. Now, there is one more anxiety-inducing factor: power. The trap relies on active cooling and monitoring. If the truck breaks down or gets stuck in traffic, the clock starts ticking. The system is designed with a grace period. If the generator fails, the thermal inertia of the liquid helium reservoir can keep the trap cold and the vacuum stable for about 4 hours. That is your window. After 4 hours, the trap warms up, the vacuum degrades, and the cargo is lost. But let's zoom out for a second. Why are we doing this? Beyond the fundamental physics questions, there is a potential application that could change lives: antiproton therapy. For decades, doctors have used radiation to kill cancer cells. The gold standard right now is proton therapy. Protons are heavy charged particles that can be tuned to stop exactly inside a tumor, sparing the healthy tissue behind it. It is far better than X-rays. But antiprotons? They can do everything protons can do, but with a lethal bonus. When an antiproton enters the body, it behaves like a proton, stopping at the tumor site. But the moment it stops, it doesn't just sit there. It captures an electron, forms a pseudoatom, and then spirals into the nucleus of a nearby cancer cell atom. And then, annihilation. The antiproton annihilates with a nucleon in the cancer cell. This releases a burst of energy, almost 2 giga-electronvolts, in the form of nuclear fragments. It effectively blows the cancer cell nucleus apart from the inside. Experiments like the ACE experiment at CERN have shown that antiprotons are up to 4 times more effective at killing cancer cells than regular protons. Plus, the annihilation releases particles called pions that fly out of the body. By detecting these pions, doctors could image the tumor in real time, verifying exactly where the beam is hitting. The reason we aren't using this today is that you can't bring a cancer patient to the experimental halls of CERN. But with a portable trap? The game changes. In the future, bottled antimatter could be driven from a production facility to hospitals in Geneva, Paris, or Milan. A local clinic wouldn't need a billion-dollar particle accelerator. They would just need a docking station to receive the trap. It is a staggering possibility. Of course, whenever you combine the words transport and antimatter, people think of the movie Angels and Demons. They picture a canister of antimatter being used as a bomb to threaten the Vatican. So is a truck carrying antimatter a rolling nuclear weapon? The answer is a definitive no. And it comes down to the numbers. The confusion comes from mixing up efficiency with quantity. Yes, antimatter annihilation is the most powerful energy release known to physics. It is 100% mass-to-energy conversion, but the amount being transported is infinitesimally small. Puma aims to transport 1 billion antiprotons. That sounds like a lot, but in terms of mass, it is roughly 1 femtogram. That is 0.0000, well, 15 zeros, and then a 1. If that entire cloud of 1 billion antiprotons were to annihilate at once, say, if the truck crashed, the energy released would be approximately 0.3 joules. 0.3 joules is roughly the energy of a small apple falling from a height of 1 meter. It is less energy than a single match flame. It wouldn't even dent the metal walls of the trap, let alone create a crater. To create a dangerous explosion, something like the Hiroshima bomb, you would need roughly 0.7 grams of antimatter. Producing that amount with current technology would take billions of years and cost more money than exists in the global economy. So the bomb risk is non-existent. The real risk is economic. If the trap fails, you lose months of scientific production and millions of dollars in research time, but you don't lose the highway. We are witnessing the beginning of the antimatter economy. The successful transport of protons in 2024 and the upcoming antiproton runs in 2025 mark a shift from static science to mobile science. Currently, if you want to study antimatter, you have to move your entire experiment, your students and your funding to a crowded hall in Geneva. Portable traps break this monopoly. We can envision a future where high-precision labs at universities in Germany, the UK, or the US could order a refill of antiprotons. They could study the particles in their own magnetically shielded, vibration-isolated basements, achieving precisions impossible at CERN. We can bring antimatter to high-intensity laser facilities or neutron sources to create new states of matter. We have moved from fearing antimatter as a sci-fi superweapon to manufacturing it, cooling it, and soon shipping it like an Amazon package. The Truckable trap is more than just a box. It is a vessel of discovery. It promises to carry us beyond the standard model of physics, and perhaps, one day, into a new era of medicine. The cargo is invisible, but its weight in the history of science is immense.